Okay, welcome everybody. Unit 1, Activity 5, Properties of Limits. It's really just going to be a review of the last couple of days of stuff, what we're doing here. A couple of properties we'll talk about, but we've been doing these types of questions, okay? So these won't be a big surprise to you. We're just going to tie up some loose ends here with limits and do some more practice with finding limits of functions. Okay, so let's get rolling on this. Functions can be combined arithmetically or by composition to create new functions, and the following laws or these properties of limits allow for finding a limit of a new function. Okay, so the following 7 properties you guys are going to have in your notes here. Okay, so the limit of a constant is just a constant, right? The limit as x approaches a of a linear variable x. Okay, so just is the value of, right? We just substitute in a for that. If I have the addition of 2 functions, I can find the limit, okay, of this new function by finding the limit of each individual function, just adding them together. Similarly, the subtraction component works. So let's say if I've got 2 terms, right, and they're either added or subtracted together, I could find the limit of the first term and add or subtract the limit of the second term. If I have a function multiplied by a constant number, I can find the limit of that function by just finding the limit of the function, then multiplying it by the constant. A product works the same way. We've seen all these applications. I'm going to go work through a couple of examples. And then the composition of a function, I can just find the limit, okay, as x approaches a of the main function, okay, and then just compose it with the next function. We'll work through all these examples and see how these work. Okay, so you have a series of a couple of questions here, and remember, this is found in 1.5, right? This lesson, if you like. Just want to show you here quickly before we get started on it. If you don't remember, it's found in the materials section, okay? And this is 1.5, so it would be right in here, okay? Let's just download that PDF. Okay, the lessons and the questions are also found in here. There's our property, 7 properties that we just did, and we're going to work through some evaluating limits. Okay, so back to our lesson here. Okay, why don't you try these on your own? Okay, so you can pause the video. I'm going to work through these answers. Every one of these is just straight old direct substitution here. Plug in. It's a continuous function. This first one's a cubic, so we can literally plug in -1 into each occurrence of x and just evaluate the function. Okay, because we're looking at the limit of the function as x approaches -1, really very close to 1, or that neighborhood idea. So I'm going to pause this, okay, and get the answers down, and you guys should do the same here, okay? Okay, so here are the evaluative limits here, okay? Straight substitution, or direct substitution I call it. Just put in -1 and we work it out to get -7. B works out to be 1. Okay, the limit of c, the limit of the function of c as x approaches 2, works out to be 3. Now you might need to review a little bit of work on logarithms from advanced functions. Okay, that logarithmic property evaluates to 2. Similarly with D, E, and F, there's trig common ratios for trig. Okay, so the sine of pi over 3 over top of the cos of pi over 3 minus 1, that's a 0, sorry. So that reduces down to 1 divided by -1, or -1. The square root of sine x as x approaches pi over 2 is 1, and then the cos of, 2 to the power of cos pi is 2 to the -1, or 1/2, and then the final one simplifies down to, or evaluates to, I should say, 1. Okay, so that's just straight substitution. And again, at any given time, if you run into a problem with straight substitution, you can graph this function in DESMOS and zoom in on and see what value the function is as x gets close to 0 here. Okay, this is what we just did. When functions are continuous, then we can simply find the value of the limit by approximating the function, or by evaluating the function at that particular point. So there's a couple more to evaluate. Okay, I'll do the first one, nice and easy. You know, it's a continuous function. Might as well roll here, and as you guys may want to pause this, I'll just work through these as well too. So x squared This is the third root of -8, which is -2. Okay, and then another logarithm would be the log. Okay, when it's base 2, and then when my answer is 4, if you'd like, okay, this review of logs here, this would be the same as this, and what's x equal? Okay, remember logarithm is just asking for the power. It's 2 in this case, and then the tan, okay, pi over 3. Pi over 3 approximately is 60 degrees, so the tan of 60 degrees works out to be root 3. Okay, let's keep rolling. Rational functions. Okay, we do a little bit of techniques when we have rational functions here, and basically if we were to go, okay, and substitute right off the bat, right, we get, let's put in the 1 here. That's because that's the first thing we should always do when we have to evaluate a limit, is just direct substitution. If we get situations like this where upon direct substitution we get, okay, 1 squared minus 1 is 0, okay, and 1 minus 1 is 0, we get a 0 over 0. This is the common 0 idea. We have to think of another way to solve it, right? So we should check for this first, but if we, okay, get this situation, we've got a 0 over 0, we have to think about an alternative way to evaluate this limit. Well, factoring is probably the first alternative technique that you do here, and realize that the numerator is just a difference of squares. Okay, and that allows me to simplify, right? So that my original limit question is actually just this, and now I can directly substitute. Okay, always go back to, okay, even after trying to factor and simplify, go back to direct substitution, trying to evaluate the limit. Again, like I said, review. Okay, we've also got when we have a radical function. Okay, a function with a radical polynomial in it. We can direct substitution again. Notice that we're going to have a 0 over 0. Okay, so how do I evaluate this? Well, we learned back at the beginning of this section conjugates, right? Okay, and the way I remove that is multiply by the conjugate. Okay, when I multiply by the conjugate, okay, a rational expression by its conjugate, I eliminate my radical, so I'm going to have root x times root x is x, minus root x plus root x is 0, then a minus 1, and in my denominator, I'm not going to multiply this necessarily, knowing full well, okay, that's going to simplify. Okay, so really the question simplifies down to what's the limit of 1 over root x plus 1, and direct substitution, yeah, perfect. Okay. Good, that's another great way to work on functions. So we've got two, well, 3 actually, so far. Okay, so we can, direct substitution. Okay, we can simplify and factor. Okay, we can multiply by the conjugate. Now we've got this change of variable technique. We've talked a little bit about this, or I've touched on this a little bit. This is complicated. I'm going to walk you through, this particular one here in a second. Okay, so find the limit as x approaches 0, of the third root of x plus 8 minus 2 all over x. Okay, well, we always try direct substitution, and notice that if we did direct substitution, we'd have 0. Third root of 8 is 2 minus 2, we'd have a 0 over 0 situation. Okay, so what do we do here? Well, we can't, third roots are pretty awkward to work with. We can't multiply by conjugate. The idea of multiplying by conjugate is to eliminate the rational, right? But we have to deal with another technique here. So let's do the change of variable here, And now how to do a change of variable. Okay, look at your function. When you have to consider a change of variable, always consider it with nth roots. So third roots, fourth roots, sixth roots. These types of change of variable, and identify the hardest part of the function, of the expression. Now, clearly, the hardest part is this most difficult piece of this function. So I'm going to let change a variable, I'm going to let m equal this expression. Okay, the most difficult part could be what you introduce the new variable to. Okay, now if I write that, I'm just going to rewrite this on this side here. Okay, now we want to work on this expression a little bit, because that's going to be what's going to happen here. Let me just start writing this. Okay, so this little piece is m, and I've got an m minus 2 here. Now in the denominator I've got an x, okay, and I don't have an x in this expression, but I do if I raise both sides to the power of 3. Okay, that's going to effectively eliminate this, right? If I have a third root and then I raise it to the power of 3, I get rid of the root sign, so I'm left with x plus 8, and if I just rearrange it a little bit more, I now have an expression for x equals m to the power of 3 minus 8. So I have x in terms of m, and that's good. That's what I want in my limit, right? Now, I have to do one more thing here, and I have to change, okay? I have to find out what m is approaching, okay? My original limit is in terms of x, and because of the change of variable technique, I'm now evaluating a limit in terms of m. So if I change m in one part of the expression, I have to change m everywhere. Okay, so as x approaches 0, what's the equivalent m approaching? Okay, well that looks hard, looks difficult to do, but it really isn't. Okay, you just go back to your little work over here and pick one of the equations, okay, and let x equal 0. Okay, let x equal 0. Let's pick this one here, x equals 0. Okay, because I have m equals. Okay, so if I let x equal 0 in this equation, okay, so 0 plus 8 is 8, and the third root of 8 is 2, m would equal 2, and that's the corresponding statement, okay, when I change the variable in my limit here. Okay, now this looks familiar. This should, okay, I've got m minus 2, and then I can factor that using my difference of cubes. I've got m squared plus 2m plus 4. It allows me to factor that, so I'm going to evaluate my limit as m approaches 2 of 1 over m squared plus 2m plus 4. And now I can do straight substitution. 1 over 2 squared and that's 1 over 4 plus 4 plus 4, or 112. Okay? That's how we do that algebraically here. Okay? And I don't have to, okay, evaluate that anymore. That's good to go. Okay. I want to go in and graph that in DESMOS. Okay, I'm just going to see what else we've got. Oh, we've got some steps here. Steps for evaluating limit. Direct substitution, just plug it in. Factor and simplify. Okay, take it if that's when we have a common 0, and then eventually when you simplify it down, you plug in your limit. Now, within this factor and simplify, okay, we might have the factor and simplify. Okay, we might also have, okay, simplifying might involve conjugates. Okay, it might have a change of variable as well too. We did each of those 3 examples, and you guys are going to have some worksheets to work on and some homework questions. If all else fails, you can graph it and evaluate, or you can make a table, okay, and just get, as we did earlier in 1.4, we made that table, and we look for, as we get closer and closer to A, we just look for convergence here, what the function's converging to. Okay, this is a homework sheet you may want to try. Okay, the answers are down here. We can work on that, and we've also got some homework questions. I'm going to pause though and finish my course by going in and going back to, okay, this question here, and I'm going to graph that in DESMOS and show you here. But let me just pause this for a second. Okay, and go. I'll be back in a second to look at the graph. Okay, here is my function. Okay, a couple of things here. This is in DESMOS. Okay, so I'm going to show you a couple of things here. If you ever have to graph a function and you realize that the function is pretty complicated. We just want to see what it looks like in order before we go and do some work on it here. Under the keyboard symbol, okay, so as you type in, okay, your inventory box here, you might need the keyboard, the screen keyboard. So when I click on that and click on the functions button, I've got trig functions, I've got stats functions, I've got, if you've taken MDM4U, there's some common stats functions, distribution, okay, so all kinds of distributions, and the miscellaneous tab is the, okay, all kinds of things here. We'll talk about log functions, and we'll talk about some of these other ones. This one right here is what I used. Okay, so the third group, okay, function was good here. Now, so this is what it looked like. Now, clearly I've got to zoom in because the original question was right here, okay, at 0 here. So I'm going to zoom in, okay, and I'm actually going to, okay, notice that it is undefined, right? Clearly, if I put a plug in 0, okay, but really close to 0, okay, and really close to 0 on the left-hand side, lead me to the same value here, okay? So, okay, if I wanted to change this to, okay, what's that, 0.001, so 1 over 1,000, okay, I'd still get that. Okay, same value here, and that's zoomed in, that's right. Okay, there's my undefined value. Okay, but there's my, okay, what did I say it was, 1/12? And I think 1/12 is about 0.08. Okay, so that's how you kind of do that, and make sure if you like to see visual math and you like to sort of see what you're actually doing algebraically, DESMOS is a great way to go here. Okay, good luck with the homework, and we'll have a live video chat today as well here, going on working on some of these questions. But I'm going to give you a couple of days to work on some limit questions.